This video is about an exact binomial test, which is another option when you have one binary variable. In this class, we usually rely on simulations to estimate probability. We don't spend a lot of time on formal probability rules. But in the very simple data scenarios we've been working with in this chapter, where we have only one binary variable, it's actually not too hard to calculate the probabilities theoretically. So I did want to emphasize that the binomial test only works in this scenario. It only works when you have one binary variable. It doesn't transfer to other scenarios, other types of data. So to understand the binomial distribution, we're going to make use of a basic probability formula called the multiplication rule. So basically the multiplication rule just says that the probability of A and B happening is the same as the probability of A times the probability of B, assuming that events A and B are independent, meaning knowing one of them doesn't help you predict the other, it doesn't affect the other. So just a very simple example of this, we could say, what's the probability of flipping heads 2 times in a row? So to put it in terms of the multiplication rule, this would be the probability of getting the first flip comes out to be heads, and the multiplication rule is about and scenarios, the second flip turns out to be heads. So to calculate that probability, we take the probability of heads in the first flip, which would be 1/2, and we multiply it times the probability of heads in the second flip, which is also 1/2, and the probability of getting heads twice in a row comes out to be 1/4. So I think that's pretty intuitive. You can also really easily here just write out all the different options that you can get, right? There's only these 4 options, and we're talking about this one. So in 1 out of the 4 options, you get heads twice in a row. So let's look at a situation that's just slightly more complicated. A student is taking a statistics quiz with 5 multiple choice questions, each with 4 answer choices, and in a moment of complete despair decides to just guess on all 5 of the questions, and X is going to represent the number correct. So first of all, what's the probability that X equals 0, meaning that the student doesn't guess any of the questions correctly? So we're going to use the multiplication rule for this. So if we think about the first question, what's the probability that they get it wrong? So one of the answers is right and the other 3 are not, and so there's a 3/4 chance that the student gets it wrong. And then it's going to be the same for the second question, and the third, and the fourth, and the fifth. And we're just multiplying these all together because if they're just guessing anyway, then these are independent events. And so we multiply them together to find the probability of getting none of the answers correct. So we're getting the answer wrong 5 times in a row, and 3/4 raised to the 5th power turns out to be 0.237. So what about the probability of getting exactly 1 answer correct? So again, there's 4 answer choices, so the probability of getting it correct is 1/4. So they got the first one correct, and then they missed the second one, 3/4 chance on any one problem of getting it wrong, and also the third, and also the fourth, and also the fifth. And so you end up with 1/4, the one that you got right, and then 3/4 raised to the 4th power for the 4 that you got wrong. But it's not quite this simple because this is assuming that they got the first question right. So this is actually assuming a particular order, right? This would be like the probability of getting correct first, and then incorrect, 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 incorrect. But that's not the only way it could happen, right? What if they got the second one correct? Now it would be 3/4 for the first one, they missed it, but they got the second one, and then missed all of the others. Remember, the condition here is that they're getting exactly 1 correct. So it comes out to the same probability, 1/4 for the one they got right, 3/4 for the ones they got wrong, and raised to the 4th power because they missed 4 questions. So then the question really becomes, how many different ways can you arrange it, right? Where can the correct answer go? How many different arrangements can you get? So we know they're getting exactly 1 correct. It could be the first, it could be the second, it could be the third, it could be the fourth, it could be the fifth. So there's 5 different ways to get exactly 1 answer correct, and all of them have the same probability. So because of that, since we have 5 ways to get 1 correct answer, we're going to take that probability that we've gotten for both of our arrangements so far, and we're going to multiply it by 5 to account for all of the different options that we could come up with. So we've got 5 for the number of arrangements. 1/4 is the probability of getting one right. If you wanted, you could even put a 1 here to illustrate that they're getting one right. 3/4 is the probability of getting it wrong. There's 4 of those. And that gives us the probability for x equals 1. And that comes out to be 0.396. So it's more likely to get 1 right than it is to get 0 right. It's more difficult when you're talking about x equals 2 or x equals 3 because there's just more arrangements, more different ways that you could get exactly 2 correct or exactly 3 correct. So it helps to have a formula that we can use every time. So if x is the number of successes in a binomial setting, binomial settings just mean the kind of situations we've been working with, where you've got binary data and everything is independent, then x has a binomial distribution with parameters n and pi. So n is the sample size, like in this case it would be the number of test questions that you're trying. Pi would be the probability of success. So we're using this symbol in a way that's pretty consistent with what we've been doing for other kinds of tests. And the possible values that x could take would be 0, you could have 0 successes, or 1, all the way up to whatever your sample size is, right? 0 to n successes. So we've already calculated the probability that x equals 0 or x equals 1, but you can do a more general x equals k with this formula. So some of this already looks familiar, right? Pi is the probability of success, which was 1/4 in our example. K is the number of successes, so when we were finding the probability that x equals 1, we put a 1 here. 1 minus pi is the probability of failure, so that was 3/4 in our example. N minus k would be the number of failures, so that's where our 4 comes from. So the only part that's still unaccounted for is this number 5, which is all the different arrangements that you have. So this is a little bit of a tricky formula. N and k in the parentheses like this, we pronounce that n choose k, and it has this formula with all the factorials in it. So in our case, this would be 5 factorial, that's our sample size. And then 1 factorial, and n minus 1 would be 4 factorial. So if you remember how factorials work, it's 5 times 4 times 3 times 2 times 1 all the way down. 1 factorial is just 1, and then 4 times 3 times 2 times 1. So here, if we cancel out the numerator and the denominator, we're left with just 5, and that's the number of arrangements that we have, the number of ways that we could get one answer correct. So we reasoned it out earlier, but if you're dealing with more complicated cases, definitely helpful to have a formula. So I wanted you to see where that formula comes from, because isn't it satisfying to see that such a complicated formula actually makes sense? But I'm not going to have you like prove it or anything like that on a quiz. I'm probably not even going to ask you to use that formula to do calculations. I just wanted you to know what the exact binomial is doing, and that it's calculating an exact probability instead of using a simulation.